Let us review in detail the separate actions which take place in an AM transmitter. The information or intelligence to be transmitted starts as sound waves which travel through air. The microphone picks up these waves and transforms them into electrical energy. Now the intelligence travels into the transmitter, taking the form of audio frequency voltages. Audio frequencies generally fall within a range of from 300 to 3,000 cycles per second. However, it is not practical to transmit these audio frequencies directly. An oscillator provides a much higher frequency. This radio frequency wave is called a carrier. By means of a modulator and one or more RF amplifiers, the amplitude variations of the audio signal and the radio frequency carrier are combined. Now the intelligence takes the form of amplitude variations in the carrier. The amplitude modulated RF carrier is fed to the antenna, from which it is radiated through space to the receiving antenna. Once the signal has left the antenna, however, it can be affected by many disturbances. For example, one such disturbance can be lightning. Let's freeze the signal at the receiver antenna and see what the interference has done to it. Our primary concern is with the amplitude variations, for they carry the intelligence. To a point, the variations are just as we transmitted them, and the AM system was working fine. But the lightning has added new variations. These are superimposed upon the variations carrying intelligence. There are many man-made devices and natural elements or occurrences that can affect the amplitude of the RF carrier. Each one adds more hash, more static, more interference. The receiving antenna will pick up both the composite RF waves from the transmitting antenna and the random noises generated by the lightning. These two will combine and distort the amplitude of our desired signal. Now a partial review of what happens in the AM receiver. The amplitude modulated RF carrier is picked up by the receiver's antenna. The receiver extracts the intelligence carried by the RF, transforms it back to an audio signal, amplifies it, and feeds it to the speaker. It emerges from the speaker as sound waves, which can be heard and understood by the human ear, unless the intelligence is smothered by interference. To see how interference gets through to the speaker, one of the receiver components, the detector or demodulator, must be examined. The detector receives the RF and transforms its amplitude variations into corresponding audio voltage variations. The detector does its job well, but blindly. It cannot think or interpret. Feed it an RF signal with constant amplitude, and there will be no output signal. Feed it a modulated RF, and it will provide an audio signal which mirrors the amplitude variations of that RF. Feed it an RF signal that has been hashed up by interference, and the audio signal will contain an accurate reproduction of that same interference. The audio signal mirrors the interfered RF signal fed into the detector. There you have a major disadvantage of AM radio. It is unable to separate the intelligence from the hash and static that appear when conditions are unfavorable. In frequency modulation, the frequency of the carrier is modulated, as evidenced by the uneven spacing of the waves, rather than the amplitude. An unmodulated carrier would be the same for FM as it is for AM. It has constant frequency and constant amplitude in its unmodulated condition. The carrier frequency, which is determined by the oscillator, is called the rest frequency. So long as there is no audio signal, the carrier is unaffected. Let's see what happens when an audio signal is applied, starting with the negative half cycle. For this illustration, the negative half cycle causes the carrier to drop below its rest frequency, as evidenced by the wider spaced waves. When the positive half cycle of the audio signal is added, it causes the carrier to rise above its rest frequency, as evidenced by the narrow space waves. This is an audio signal of one complete cycle with a corresponding frequency modulated RF wave underneath it. A variation of the amplitude in the audio signal is accurately reflected by a frequency variation or modulation in the RF carrier. The negative half cycle of the audio made the carrier drop below rest frequency, And the positive half cycle of the audio made the carrier rise above rest frequency. The carrier's ability to reflect the amplitude of the audio signal can be easily visualized. But how will it record changes in the frequency of the audio signal? This question can be answered by changing the frequency of the audio signal and observing the results in the carrier. If the frequency of the audio signal is doubled, then in the same period of time, there will be 2 complete cycles instead of 1. Note that the amplitude of the 2-cycle audio signal is the same as the amplitude of the single-cycle audio signal. Now let's see what this has done to the carrier. As before, the carrier responded to the amplitude of the negative half cycles by dropping below rest frequency, and the carrier responded to the amplitude of the positive half cycles by rising above rest frequency. Thus, the carrier has moved above rest frequency twice as often in the same interval of time, and the carrier has moved below rest frequency twice as often in the same period of time in response to the doubling of the audio signal frequency. But since the amplitude of the audio signal was not changed, the distance above and below rest frequency traveled by the carrier has remained constant. A typical FM channel, 40 megacycles, would be located here. This is the rest frequency of the channel. When the carrier is frequency modulated, it will move above and below its rest frequency. In other words, it will need room on the spectrum to carry its frequency variations. A typical amount of room might be 15 kilocycles above rest and 15 kilocycles below rest. To avoid conflict with adjacent FM channels, 10 kilocycle guard bands are added on each end. This typical channel will allow the carrier a 15 kilocycle deviation above and below its rest frequency. Add to this the 10 kilocycles on each end for guard bands, and the total band width is 50 kilocycles. The 50 kilocycles band width is not a standard. All FM transmitters do not have the same deviations. It will vary in accordance with the equipment's design and mission, but the principles under study apply to any and all FM transmitters. Ordinarily, an audio frequency wave is visualized horizontally like this. But in order to see more clearly its modulating effect on the carrier, let's shift it about and direct it at the channel. Notice that the amount of deviation above and below rest frequency is determined by the amplitude of the modulating signal. If we raise or lower the frequency of the modulating signal, we increase or decrease only the speed at which the carrier moves above and below its rest frequency. We do not change the extent of its deviations. Only by changing the amplitude of the modulating signal do we change, decrease, or increase the extent of deviation above and below rest. FM circuitry is designed so that maximum amplitude of the modulating signal will cause the carrier to deviate to the maximum frequency range assigned to it. Note that this does not include the guard band, or in other words, the carrier will swing as far above and below its rest frequency as it can go. Now that we are familiar with the basic principles of FM, let's make a quick rundown of the components that make it possible. The transmitter's components are similar in name to their AM equivalents, and they do similar jobs, but in a different way. The audio circuits provide the audio frequency signal, which is fed to the modulator. The action of the modulator is such that the output of the oscillator is a frequency-modulated RF wave. The components of the FM receiver are a bit more complex, for they have an additional factor to contend with. The incoming carrier contains intelligence in the form of frequency variations, but it also contains amplitude distortions, hash, and static. These we do not want. Since these distortions are located along the amplitude peaks of the carrier, we can eliminate them by eliminating the peaks. This is accomplished by a circuit that clips the peaks by limiting the amount of current flow induced by the positive and negative alternations of the carrier. This stage is called a limiter. Its output is a wave that still carries the intelligence in the form of frequency variations, but it no longer includes the extremes of amplitude that carried any interference picked up during transmission. The next step is to extract the intelligence, to change the frequency variations back into audio frequency voltage variations. which we can then amplify and feed to a speaker. In an FM receiver, this is the function of the demodulator or discriminator. You might say that the discriminator in FM is the rough equivalent of the detector in an AM receiver. Feed the frequency modulated carrier into the discriminator and its output will be an audio frequency voltage. Feed it an RF signal with constant frequency and there will be no output signal. All FM discriminators do the same job, but not all do it the same way. For a briefing in the fundamentals of the discriminator, let's take a simplified look at how this typical discriminator does its job. We are primarily concerned with two things, the wave and the discriminator. In place of the wave, this vertical line will represent the range of input frequencies to the discriminator. This horizontal line represents the frequency range of the carrier. It also will represent rest frequencies. This line will represent the maximum deviation above rest frequency, and this line will represent the maximum deviation below rest frequency. On this scale, we will see the frequency of the carrier as it arrives at the discriminator. Now we'll add another scale. This one will measure the voltages of the audio frequency signal coming from the discriminator's output. We'll add 3 dotted lines. One will represent 0 voltage. A second line will represent peak positive voltage, and a third will represent peak negative voltage. When the carrier is at rest frequency, the audio output voltage of the discriminator will be 0. Thus, an unmodulated carrier results in no audio signal. For this illustration, when the carrier deviates above rest frequency, the circuitry of the discriminator generates a positive voltage. When the carrier drops back down to rest frequency, the positive voltage gradually diminishes. When the carrier deviates below rest frequency, the discriminator responds with a negative voltage at its output. When the carrier moves back up to rest frequency, the negative voltage diminishes to 0. Now watch the continuous action. Note that the amplitude of the audio signal is an accurate reflection of the amount of the carrier's deviation above and below rest frequency. Also note that the frequency of the audio signal is an accurate reflection of the rate or speed at which the carrier registers its deviations. Thus, the audio signal's two characteristics, its amplitude and its frequency, are an accurate reflection of the carrier's amount of deviation and rate of deviation. In this way, we have transformed an RF carrier's frequency variations back into an audio frequency signal. From the discriminator, the audio goes into an audio amplifier, and from there to a speaker or headphones. The intelligence has completed the trip from transmitter to receiver.